Welcome students, welcome to the second episode on this graph basic series. So in the first episode I asked you one question in the end, that is tree a kind of a graph? So the answer is yes, a tree is a kind of graph, because for example, let's say if we take this graph, right, and this graph, if we take this graph and if I just remove a few edges from it, right, especially those edges which are forming loop, so this one and this one, let's say it could be other edges also, but just for sake of example, so what it would turn into, it would turn into in this graph. And can you recognize this graph? Yes, this graph is a binary tree, right? So the point is that a tree is a graph without loops, right? So if I have a loop here, it is still a graph, but it is no more a tree. So this is one important thing you need to keep in mind. Now that brings us to the second part of this lecture, which is basically your representation of graphs. So before the representation of graph, we'll just digress a bit into type of graph. So there are multiple classification in which a graph can be classified. One classification is a directed graph and an undirected graph. So as you can see here, this is the case of your undirected graph, and this is your directed graph. So what is the difference? Difference is very simple. So here you can see in this case the edge between any two nodes, right, is not a directed one, and here it is a directed one. By direction we means that the edge has a direction, so that's why it is a directed. So here if you see the edge is going from 1 to 2, right? So you can go from 1 to 2, but you cannot come back from 2 to 1. But in this case, when edge has no direction, so we can assume this edge as a bidirectional edge, right? So this edge from 1 to 2 can go from 1 to 2 and from 2 to 1 as well. It's the same edge, right? So it's just both ways, it's identical, right? So if that is the case, so it becomes an undirected graph, and if the edges in the graph has direction, then it becomes a directed graph. So in case of a directed graph, you need to keep into mind, so these two edges, if you see here, A to B and B to A, they are not same, right? So that's the only thing you need to keep in mind for now for undirected and directed graph. Now having gone through a kind of graph, now let's come back to the representation of graphs. So it's fine, like we got to know that what graphs are. In case of a computer science, they are but nothing but a collection of nodes which are connected by some edges, right? And finally we represent graph basically as a graph mathematically as nothing but a collection of your vertices and your edges, right? No, but how do we represent it in the language of computer, that in any programming language, right? Let's say C, for example. That should come into your mind. How would you represent two nodes connected by an edge, right? A very simple case. So if there's just two nodes and they are connected by an edge, how would you represent in programming language? So there are two representations. One is called adjacency matrix, another is called adjacency list. So basically you need to keep these two things in mind. So matrix representation and list representation, because you know the adjacency is common to both. So usually people will ask you that what's the matrix representation of the graph, how the complexity will differ if it's not a matrix representation, it's a list representation. So you need to keep these two things in mind. One is matrix representation and another is list representation. So as the name suggests, so let's go into the first implementation, matrix implementation. So as the name suggests, matrix implementation means you will represent graph in form of a matrix, right? So for example, if this is your graph, now how would you represent it in form of a matrix? So what we will do, so let's say that this graph has n vertex, right? So n is the number of vertex, right? So in this case, what is n? 1, 1, 2, 3, 4 and 5, right? So we have to make a matrix of n cross n, right? So here I have made the matrix of n cross n. Now how do you represent? So matrix is very easy, right? In C language by now you would have really worked on matrices, right? So add two matrices. First of all, how to declare a matrices, right? It's nothing but a two-dimensional array, right? Two-dimensional array is a matrix, right? Representation. How to populate it, how to get a particular value. So you just use two for loops, right? For any operation in matrices usually, right? And stuff like that. So you know about the matrix, right? Two-dimensional array. So basically it's a two-dimensional array. So in two-dimensional array, you will represent a graph. Now how? That's very simple also. So for example, if how will I do it? So first of all, I'll go to the row 1. So here my row 1 represent, and these are my columns, right? So here row 1 represents my vertex 1, right? And the corresponding column here will represent that how can I reach, is there an edge to these vertices? So let's see, let's see, and then you'll understand it. So from 1 to 1, is there any edge from 1 to 1? No. So what I'll put 0 here, right? Had there been some edge like this, then I would have not put 0, right? But there is no edge such. Now from 1 to 2, is there any edge? Yes, there is an edge. And let me do one more thing. Let me just remove these numbers. Sorry, they will come into picture very soon. As of now, there are no. Actually, these are weights of an edge. So something like this, right? Now from 1 to 2, is there an edge? Yes, there is an edge. So I'll just put here 1. From 1 to 3, is there any edge? No, there is no direct edge. So I'll put 0. From 1 to 4, is there any edge? No, no direct edge. I'll again put 0. From 1 to 5, yes. So I'll put 1, right? Now let's do for again. So what we'll do here, now we'll come to row 2. We'll go to vertex 2 because it is a representative of vertex 2. 2 to 1, is there an edge? Yes, there is an edge. I'll put 1. 2 to 2, is there any edge? No, I'll put 0. 2 to 3, yes, I'll put 1. 2 to 4, again yes, I'll put 1. 2 to 5, yes, again I'll put 1, right? In this way you can go. Now I'll try to be more quick over it. So there is one trick, one small trick. What you do, you go to vertex 3 now, right? So, and you just see how many edges are emanating out of 3 to its neighbor. So there are 2, right? Only for 2, node number 2, and for node number 4 we have 1 edge each. So just put 1 there. So for under 2, 3 to 2, 1, and 3 here and 4 here, and I'll put here 1. Rest automatically 0. Similarly for 4, if you'll see, I'm just pausing here for a moment. Try to fill it by yourself. Yes. So if we try to fill, so now from 4 you can see you have edge to 5, 3 and 2. So 5, 3, 2, rest will be 0. From 5 to 1 to 2 to 4, to 1 to 2 to 4, and rest, are there any edges? No. For 3 there is no edge, to 5 itself there is no edge, so we'll have 0. And oh, I'm sorry, I've put here 4. Oh, what I've done, I'm so sorry. For 5, let's begin again. So for 5 you have an edge to 1, so here it will be 1, right? For 2 and 4 are there also edges. So for 2 and for 1, sorry, I'm saying for 4, and for 3 and 5 there are no edges, so it will be 0 and 0. My bad, I apologize for this mistake. So yeah, so now this is the representation of your this undirected graph in a matrix form. That's it. So this matrix now represent this graph. So these, your basically these things represent your vertices, and these values, the values inside here, they represent your edge, whether there is an edge between two corresponding vertex or not, right? So now let's do one again example for a directed graph. Very similar thing, nothing you have to do, probably you can do it by yourself also. So let's start. So very simple. Now here, since there is an edge, right, directed edge, so it's not a bidirectional edge, right? So from 1 to 2 there is an edge, 1 to 1 there is no edge, here there is no edge, so I'll put here just 0. From 1 to 2 there is a directed edge, I'll put 1 here. From 1 to 3, is there any edge? No, 0. From 1 to 4, no, 0. And from 1 to 5, again yes, so I'll put here 1. Now be careful here. Now for 2 and 1, so now what we'll analyze, that from 2 to 1, is there any directed edge? No, right? So here we'll put 0. Now had it been a normal undirected edge, so this would also have been 1, but now it's 0, right? From 2 to 2, 0. Again you can take that trick. Now from 2, just see which nodes, from to which nodes edge is emanating from 2. So I think it's 3 and 5. So for 3 and 5 we'll put 1 and rest 0. Now I'll pause a bit, try to complete it by yourself, and then I will share the solution with you. Okay, now for 3, similar thing. 3, are there any edges which is emanating from 3? No. So just put 0, 0, 0, 0 and 0. See the same thing for 4. Oops, sorry. See the same thing for 4. So for 4, from 4, edges which is emanating from 4 is only 1, right? That is 4 to 3. So 4 to 3, 1 edge and rest is 0. Again emphasizing, this edge you will not count because it is terminating at 4. So this will come into picture when we'll consider vertex 5. Now from 5, how many edges are going emanating from 5? Only 1 edge, and 2 are terminating, so will not they not be accounted for. So only 1 edge is there from 5 to 4. So from 5 to 4 we'll put 1 and rest is all 0, right? So now this is this matrix basically now represent this particular directed graph, right? So isn't it very very nice that from this simple matrix you can represent a graph, right? Now the question would be, what if there are weights to this edges? So weights means, let's suppose if 1 and 2 is represented by a city, right, a very practical application, this edge is representing a distance, let's say 4 kilometer. This 1 to 5 is representing another distance, let's say 5 kilometers. This is representing, I'm just making up numbers by myself, 1, this is 6, this is again 2, right? So now how do we account for these weights to edges? Could you think over it? It's very simple. All you need to do, instead of entering 1 wherever there was an edge, what you will do is you will just put the weight of the edge. So for 1 to 2 there is an edge with the weight 4. So all you need to do is just put 4 here. That's it. Done. From 1 to 5 there is an edge whose value is 5. So all you need to do is put here 5. Now could you complete rest of the rest of the matrix by yourself? Just do it. I'll pause for a moment and then I'll share the solution. Okay. Now how do we solve? So let me do one thing. Let me just remove these ones first. And now I'll just put the weight of the edges. So for 2 to 3 it will be 1. For 2 to 5 it is 2. Now for 3 it's all 0. For 4 to 3 it's 2. For 5 to 4 it's 6. That's it, done. And I think you by now you'll be just guessing. The same thing we'll do here, right? So for the sake of brevity I am not doing it here, but for example let's say if these have also some weights, In that case, what you would have done, just remove these ones and fill it accordingly, right? So for example, in this case, I'll just do for the row 1. So let me remove this, and what it would be here, from 1 to 2 there is an edge of weight 2, from 1 to 5 there is edge of weight 3, right? So same thing, so on and so forth, right? So that's all to it, seriously. And now I'll ask you one question. So you must be observing here that though we have made this matrix, and the matrix is n cross n, right, where n is the number of vertices in a graph. Now you must be observing that lot of the space here is what? Is vacant, right? All this space is vacant, right? And so first of all, these kind of matrices, they are called sparse matrix, right? And you would see that, okay, this much space is being literally wasted, right? Now can we conserve it probably with some other representation? Yes. Now that is taking us to the next representation of our graph, that is list representation, right? So this is precisely one disadvantage of this representation, that in case of a sparse matrix, when your graph is not dense. And one more definition you will very come across: dense graph and non-dense graph. So what do we mean by dense graphs? So dense graphs are, for example, if I have 4 nodes here, right, this way I can connect them, right? These are the minimum edges which will be required, like side, so 4 vertex, 3 edges. But there could also be a case where each node is connected to every other node, right? For example, A, B, C, D. So A node is directly connected to B, C, D as well. B is also connected to A, C. B is also connected to A, C and D, right? So in this case, you will see that the edges are, there are a lot of number of edges, and this matrix will no longer be filled with zeros. It will no longer be a sparse matrix, right? So in that case, the graph becomes dense, right? So I have now 2 questions for you. I think we should now terminate this video. So in the next lecture, first we'll discuss the list representation, and for you there is one quiz question that you should solve. So this is your directed graph, and this is the matrix representation which I need you to fill. So that you will do. My second question to you is that if there are n vertex in a graph, right? So what could be the maximum number of edges possible? And that function you have to represent in form of n, which is the vertex, right? So I mean, like, whether it will be a quadratic function, whether it would be linear function. So how number of edges are depending upon the number of vertex, if we are assuming that the graph is dense, or what we are assuming that for every vertex is connected to every other vertex in a graph. Just think over it. It's a simple maths question based upon permutation and combination. You must have done it in mathematics in your high school, or probably first year of mathematics course in your college. So I'll see you in the next lecture with definitely the answers of these 2 questions. Till then, you can work around them, search the net, think it over. Thank you very much.